Hi friends, so this is part 2 in a series of videos of how to compute the time complexity, especially during interviews and in real life. So this is not related to research or this is not related to academics. So this is something which is very intuitive in nature. So how do you find the time complexity in a very intuitive way without using any equation, without using any formula, etc. In the part 1 we discussed how to compute the time complexities of questions which are related to arrays, array data structure. In this video we are going to discuss how to compute the time complexity in problems which uses binary tree data structure. So we are considering this binary tree. Incidentally, this is a binary search tree, but we will look at both the cases, when the tree is binary search tree and when the tree is a normal general normal binary tree. And we are focusing only on binary trees. We are not focusing on general tree. We are not focusing on multivariate tree or m-way tree or b plus tree. We are only focusing on binary trees in this video. All right, so let's start. So normally, the first thing that we should look for is that are we traversing the entire tree or are we traversing part of the tree? So are we visiting each and every node? This is probably the first thing that we should look at. How many nodes are we visiting? Are we visiting every node? So basically we should have a counter k which says that k is the number of nodes that we are visiting. So this may not be equal to, so let's call it n instead of k, just so that we follow the normal convention. So n may not necessarily be the number of nodes in the binary tree. N essentially means the number of nodes that we end up traversing in the worst case. All right. Second thing that we should look for is what is the amount of work done, what is the time that we are taking at each node. So time taken at each node. Let's say this time is k. So now you guessed it right. So the total time taken is on the order of n into k. Let me repeat it. N is the number of nodes that we are visiting as part of our problem solving, which may not be necessarily equal to the total number of nodes in the tree. And k is the work that we are doing or the time that we are taking at each node. So let's consider the pre-order traversal, this first code. So this is a normal pre-order traversal of the function, pre-order traversal of a binary tree. In pre-order traversal, what we do is that first we print the data at the root. So first we print 5, then we traverse the left subtree in pre-order, and then we traverse the right subtree in pre-order. So traversing the left subtree in pre-order means that we will first visit 3, then 1, then 4. So now we have visited the left, we have traversed the entire left subtree of 5. After this, we will traverse the right subtree of 5 in pre-order, which means first the root of the right subtree, that is 10, then the left child of right subtree, 8, and then 20. So this is root, this is the entire left subtree, and this is the entire right subtree, and that follows the same logic is applied in the left subtree, that we follow the root of the left subtree, then left child of left subtree, and right child of left subtree. Here, if you notice, we are visiting each and every node only once, and when we are visiting that node, we are taking constant time at that node. For every node there is a function call, and at each of the function call we are first checking a condition, then we are printing the data of that node, and then we are calling two functions for that node. Function call is a constant time operation. That function may not take constant time, but calling the function is a constant time operation. So at every node we are taking constant time. Total number of nodes are, let's say, n, so the total time taken is on the order of n. Now let's come to the memory, or maybe we'll come to the memory consumption later. So the total time that we are taking in pre-order traversal is on the order of n, because we are visiting each and every node, and at every node we are taking constant amount of time. Let's consider this search algorithm. So in this search algorithm, we are searching the entire tree. We are not so this is a general search algorithm. This is not a search algorithm for binary search tree, right? We will come to it later. So if it is a normal tree, then how do we search in the tree? First we check, let's say we are looking for a value 3. So we check whether root is equal to 3 or not. So 5 is not equal to 3. Maybe this is not a good example because this is a binary search tree and we are talking about normal tree. So let's say I have a tree like this. So let's say the value that I am looking for is 3. So if I am looking for 3, I will first compare 5 with 3. 5 is not equal to 3. So what I will do is I will search the entire left subtree. So if I find the value in the left subtree, then this will return true. But in this case, since 3 is not present in the left subtree, so this will return false. So if the value is not found in the left subtree, then we will search the right subtree. And if the value is found in the right subtree, then right subtree will return true, otherwise it will return false. In this case, it will return true, and at the root, we will return true when we find the value either in the left subtree or in the right subtree. So let me repeat it. First, we are checking data of root, whether this is equal to value or not. If this is equal to value, then we don't need to search the left subtree and right subtree. We have already found the value. If the data of root is not equal to value, then we search the left subtree, and remember there is a short circuit evaluation. So if the if the value is found in the left subtree, which means that if this is true, then we are not calling the right subtree. So we will search in the right subtree only when the value is not found in the left subtree because of short circuit evaluation. So if either the value is found in the left subtree or the value is found in the right subtree, then we return true, otherwise we return false. Here, let's consider both the cases. Let's consider the best case and the worst case. In the best case, what will happen is that, let's say we are looking for 5. So if we are looking for 5, then 5 is found at the root itself, and we don't need to go deeper into either the left subtree or the right subtree. So we will just return true from the first iteration of the function, and the function and no more iteration of the function will be called. The function will not be called for left and right subtree. So it means that in the best case, when data is at the root, then because the function is called only once, so we will take time equal to only one function call, and in one function call we are taking constant time. So total time taken is constant. So this is the best case. And in the worst case, what will happen is if the data is not present in the tree. So if the data is not present in the tree, let's say we are searching for 12. So 12 is not present in the tree. So first we will search the entire left subtree. How do you search the entire left subtree? You will visit each and every node and check the data of that node against the value that we are looking for. So if the so essentially we are visiting each and every node in the left subtree. Similarly, we are visiting each and every node in the right subtree. So since we are visiting each and every node and we are taking constant time to check whether data is present at that particular node or not. So in the worst case, where we end up visiting every node of the tree, we end up taking on the order of n time, right? So this is the worst case time and this is the best case time. Here the timings are different because the visiting of every node is conditional depending on whether the value is found earlier or not. All right. In case of pre-order, because we are unconditionally visiting each and every node, so the time taken is on the order of n, which is constant. Now let's look at the binary search tree. So let's say we are searching in a binary search tree, and this is the binary search tree. So if we are looking for 10 in this binary search tree, then first we compare the data of the root. So 5 is less than 10. If 5 is less than 10, we know that all the values in the left subtree are less than root, and all the nodes in the right subtree are greater than root. So if we are searching for 10 and 10 is greater than 5, so it means that without visiting the left subtree, we can discard the presence of value in the left subtree. So we can say that 10 cannot be present in the left subtree without even visiting the left subtree, right? Or if we are searching for, let's say, 2, then we can say that 2 can only be present in the left subtree. It is impossible for 2 be present in the right subtree because this is a binary search tree. So without visiting the right subtree, we are discarding the entire right subtree. So we are discarding the entire right subtree. So either we are discarding the left subtree or we are discarding the right subtree. In other way, either we are searching only in the left subtree or we are searching only in the right subtree. And this thing applies for all the levels. So when you are at 3, if we are looking for 2, then we will discard the right side of 3. Similarly, when we are at 10 and if we are searching for, let's say, 25, then we will discard the right subtree. And if we are looking for, sorry, if we are searching for 25, then we will discard the left subtree, because 25 cannot be present on the left side of 10. Alright, so in this case, initially I have n nodes. Then in the second iteration, because I am going to either the left subtree or the right subtree, we will have only n by 2 nodes. Then in the next iteration, we will have only n by 2 square nodes. Then in the next iteration, we will have only n by 2 cube nodes, and so on. So we keep on searching as long as n by 2 raised to power k becomes equal to 1 or null, right? So we are so number of levels, and at each level we are taking constant time. So at each point we are taking constant time. So the total time taken is equal to number of these levels, which is k, that is log of n. So that's why binary search takes on the order of log n in the worst case. Remember, we are only talking about the worst case. The best case is the same. The best case is when we are searching for 5, which is present at the root itself, right? So the best case is on the order of 1 and the worst case is on the order of log n. Now here is a catch. This on the order of log n has a implicit assumption that binary tree is balanced, right? We have equal number of nodes, almost equal number of nodes in the left and the right subtree. Let's say if my binary search tree is like this. So this is also a binary search tree where the left child of every node is null. So if the left child of every node is null, node has only the right child, and let's say I am looking for 7. Then I end up traversing each and every node of this tree, and we are essentially traversing this tree like a linked list. So we are going to each and every node of this tree. So this will take on the order of n time. So on the order of log n time was when the tree is balanced and left subtree and right subtree has equal number of nodes. So we are discarding almost half of the nodes at every step. But here we are not discarding even a single node. Let's say if we are searching for 7, then we will ignore the left side of 1, but left side of 1 does not have a node. So we are not ignoring any node, right? So we end up visiting all of these nodes. So if we end up visiting all of these nodes, then the time taken is on the order of n, right? So let me rephrase the answer. That should be that how much time are we taking to search in a binary search tree? So if it is a normal binary search tree which is not balanced, then we are taking on the order of n time. But if it is a balanced binary search tree, then we are taking on the order of log n time. And in the industry, it is assumed during the interview, you can make this assumption that my tree is always balanced. So for interview, strictly for interview purpose, you can say that the algorithm will take on the order of log n time. And in case the interviewer counter question you that how will it take on the order of log n time, is it the worst case complexity, then you can say that I am assuming the binary search tree to be balanced. So this is a very fair assumption to be made during the interview. Alright, now let's come to the memory complexity. How much memory are we taking? So memory depends on basically how the function calls are being made. Let's consider the pre-order traversal. So in case of pre-order traversal, first we are calling the function for r equal to 5. Then we are calling the function for r equal to 3. Then we are calling the function for r equal to 1. Then we are calling the function for r equal to null. So each of these stack frame, so there are 4 stack frames, and each of these stack frame takes constant amount of memory. So the total amount of memory up to this point is on the order of h, where h is the height of the tree. right? Now when this null returns, then we will call the function for right child of 1, but the memory allocated to right child of 1 will be at the same place where the memory was allocated for left child of 1. So it means that we are not taking any extra memory for this, right? We are consuming the same amount of memory. For example, when we call the function for left child of 5, then let's say the activation record or the stack frame is allocated here. When this function returns, then we will call the function for right child of 5, and a new activation record will be created at this point, at the same point, with r equal to 10. So when we are in the left child, the memory is not allocated for the right child, and when we are in the right child, the recursion for left child has already completed. So we in most of the cases for binary tree problems, the memory consumption, if we are using a recursive algorithm, the memory consumption is usually equal to the height of the tree, because when the recursion for left subtree completes, only then the recursion for right subtree starts. So when the memory allocated for the recursion of left subtree is relinquished, then the memory allocation for right subtree recursion starts, so which end up using the same memory. So so the total memory consumption is equal to the height of the tree. All right, I hope this video is helpful. So we have not considered some of the cases where, let's say, I am traversing the binary tree in level order traversal. So if I am traversing the binary tree in level order traversal, then I am using an extra queue, but I am not using recursion. So if I am not using recursion, then the way of computing the time complexity changes. So maybe I'll cover it in future videos. If you like this video, please hit the like button and subscribe to our YouTube channel. Thank you.